Hello, my name is Olivia McGee, and I'm a junior at Reed College.
And my name is Gopal Goel, and I'm a freshman at MIT.
And today we're going to talk about a theorem concerning the weighted chains in the circular Bruhat order.
So our main object of study is a combinatorial object known as the circular Bruhat order. This object is motivated from the geometry of the non-negative Grassmannian, which we'll talk about in the talk. But the main goal of our project was to extend a result of Stembridge about maximal chains in the ordinary Bruhat order to the circular Bruhat order.
So as Gopal said, our theorem itself is purely combinatorial, but I'm going to start by talking to you guys about a geometric object called the real Grassmannian, which is an object that parameterizes all k-dimensional subspaces of Rn. It is useful to think about points in GRKN as k by n matrices of rank k, and these are equivalence classes of matrices where two matrices are equivalent if one can be obtained from the other via row operations. So as an example, we have this 2x4 matrix, so it lives in GR24, and then the rows of this matrix act as basis vectors for the subspace that they span. The object that we are actually interested in is a totally non-negative Grassmannian. This is the subset of matrices in the real Grassmannian that have totally non-negative Plücker coordinates. The Plücker coordinates of a matrix is a list of its maximal minors, an ordered list of its maximal minors, which are the determinants of its k by k submatrices. So as an example here for our 2x4 matrix, there will be six Plücker coordinates. The first Plücker coordinate is determined by the first two columns, and the last Plücker coordinate is the determinant of the submatrix with the last two columns 3 and 4. So the geometry of the totally non-negative Grassmannian can be complicated, so it's useful to decompose it into smaller pieces, and we call these pieces positoid cells. Positoid cells are determined by a subset M contained in the set of all subsets of size k in a subset of the numbers 1 through n. So each element I in M is a subset of size k. Then the positoid cell associated with this subset M is the set of all matrices in the totally non-negative Grassmannian that have positive Plücker coordinates in the column set I, if and only if I is in M. So all other Plücker coordinates are equal to 0. Then we can build a totally non-negative Grassmannian by gluing together these positoid cells. And each positoid cell is isomorphic to a ball, and they can be of varying dimension, all less than or equal to n. So as an example, I'm going to talk about GR13 totally non-negative. So recall that GR13 is the set of all one-dimensional subspaces in 3 space, which can be represented as lines through the origin in 3 space. And if you think about it, every line through the origin crosses or intersects the unit sphere at exactly 2 places. However, we are only interested in the lines that contain totally non-negative points. And these lines are in 1-to-1 correspondence with the points in this purple region, where A1, A2, and A3 are all totally non-negative. And this purple region translates easily to a triangle, as pictured on the right. This triangle is a convenient way to see how these positoid cells can be glued together to create a totally non-negative Grassmannian. So we have 3 zero-dimensional positoid cells, P1, P2, and P3, 3 one-dimensional, and 1 two-dimensional. And this post-it on the left is the gluing instructions for how to put these positoid cells together. So P1 is glued to P12 and P13, which are both glued to P123, and so on. So this post-it on the left is isomorphic to the post-it that our theorem is concerned with, which is the circular Bruhat order.
Yeah, so before continuing, let's define what a poset is along with some related terminology. So poset stands for partially ordered set, and that's basically an inequality relation on a set which satisfies some natural axioms. And the axioms listed here are the axioms that a partial order has to satisfy. A cover is essentially an inequality relation which cannot be refined further. So for example, we have x less than or equal to y is a cover if there's no z that you can insert between x and y. Now, a saturated chain is simply a chain of cover relations. Yeah. Now, the ordinary Bruhat order is a partial order on the set of permutations of size n. Recall that an inversion of a permutation is a pair of elements in the permutation which are out of order. And now the cover relations of the Bruhat order are essentially given by swaps, which increase the number of inversions by exactly 1. So for example, in the picture below, we have the graphs of 2 permutations. And note that if you swap the second and the sixth elements, you can get from the left permutation to the right permutation. Now, since the box spanned by the second and the sixth elements is empty, this actually means that that exactly 1 inversion is added when you perform the swap, which means that this is actually a cover relation in the Bruhat order. So here's a picture of the Bruhat order on permutations of size 4. And the way this diagram works is that each segment corresponds to a cover relation, and the lower element is smaller than the higher element in the inequality relation. Now note that the bottommost element is always 1, 2, 3, 4, which has 0 inversions, and the topmost element is 4, 3, 2, 1, which has 4, choose 2, or 6, which is the maximum number of possible inversions. So now to describe Stemberger's result, we need to assign weights to each cover relation. So fixed indeterminates alpha 1 to alpha sub n minus 1. And now for a cover relation which swaps the ith and the jth elements, define its weight to be the sum of alpha I to alpha sub j minus 1. So in our previous example, we had a cover relation which swapped the second and the sixth elements. So therefore, the weight of that cover relation is alpha 2 plus alpha 3 plus alpha 4 plus alpha 5. So now the weight of a saturated chain is simply the product of the weights of its individual cover relations. So Stemberger's main theorem states that the sum of the weights of all maximal chains in the Bruhat order, and recall that a maximal chain essentially is a saturated chain which goes from the bottommost element to the topmost element. So the sum of the weights of all these chains is given by the formula shown here. And the interesting thing to note about this is that it factors completely into linear pieces.
So Stemberger was concerned with regular permutations, and our theorem is actually concerned with something called decorated permutations, which are easily explained through an example as shown here. Each decorated permutation can be represented with a chord diagram, which is what this is. And you can read this chord diagram as 1 maps to 4 and 2 maps to itself, and so on. And as you might notice, there's something a little different about the 2, and that is because each fixed point in the decorated permutation is colored either black or white. So 2 is colored white, 5 is colored black. And we can represent these with these counterclockwise and clockwise arrows. An important statistic about decorated permutations is its anti-exceedances. We call a number I an anti-exceedance if its inverse is greater than I, or if I is a white fixed point. So we have 3 anti-exceedances in this particular decorated permutation pi. They are boxed. 1 is an anti-exceedance because its inverse is 7, which is greater than 1. And there's a similar story for 3, and then 2 is a white fixed point.
Yeah. So now to talk about the cover relations of the circular Bruhat order, we have to talk about these things called alignments and crossings. So for now, just focus on the leftmost column. And an alignment, so an alignment is essentially a pair of non-crossing arrows, which are not necessarily parallel, but they point in the same direction. And a crossing is a pair of crossing arrows. And the other 3 columns, so that's what I did was what I described was the picture in the first column. And then the other three columns describe degenerate cases of alignments and crossings. So for example, if one of your chords has a fixed point, or if the endpoints of the arrows touch in a crossing, things like that. Yeah, so but that's what alignments and crossings are. Now, a simple alignment is essentially an alignment such that the following two chords have no arrows in between them. So what I mean is that this picture on the right here is an example of an alignment. And if these two red chords have no arrows in between them, then we call this alignment a simple alignment. Now, the cover relations in the circular Bruhat order are exactly swaps which turn simple alignments into crossings. So the picture above shows that we can turn the simple alignment into a crossing. And it's easy to check that this operation preserves the number of anti-exceedances, but it may change the set of anti-exceedances, which will be important later.
So explicitly, the circular Bruhat order is the poset consisting of decorated permutations on n elements with k anti-exceedances. And as Gopal said, the cover relations are these simple swaps that either subtract or add exactly one alignment. So the unique top element of CPKN has the least number of alignments, and it is defined by I maps to I plus k mod n. Then there are n choose k bottom elements, which are all iterations of the identity permutation, where you choose exactly k elements to be white fixed points. So to get to our main theorem, we have to talk about this set of anti-exceedances, which we'll denote as I of pi. Then the weight of a covering is the same as it was before if this I of pi changes during this cover relation. And then we have this circular analog or this wraparound weight if the I of pi changes stays the same. So our main theorem is that the sum of the weights of all maximal chains in the circular Bruhat order is this formula below, where Fkn is a constant dependent on n and k. And again, note that this formula factors into linear terms. So to understand Fkn, we have to talk a little bit about Young tableau, which is this arrangement of boxes where the rows are of non-increasing length. And then standard Young tableau have the added condition that the numbers in each row and column are increasing. So I've given two examples here. The one on the left is pretty trivial. This is a more random example of what a standard Young tableau could look like. Then the sequence Fkn counts the number of unique standard Young tableau that can fit into a k by n minus k rectangle.
Yeah. So we'll just so here's a picture of the circular Bruhat order on circular permutations of size 3 with 2 anti-exceedances. So here's an example of a maximal chain in the order. And note that the weights of the cover relations are alpha 2 and alpha 1 plus alpha 2. So the weight of the chain is alpha 2 times alpha 1 plus alpha 2. And now if you add these weights of these chains over all possible chains, maximal chains, then we see that the answer factors exactly as our theorem predicts. Now note that F2 comma 3 is equal to 1 because there's only one valid Young tableau for a 2 by 1 rectangle. Yeah, so let me just quickly go over the proof idea behind our theorem. So the first main idea is that it suffices to find a function delta on circular permutations that satisfies the following recursion. And one can then use this recursion and use a double counting argument with it to factor the chain sum as per our theorem. So call a cover relation good if it preserves a set of anti-exceedances. And recall that these are the same ones which have a wraparound weight. And it turns out that we can characterize this function delta in terms of saturated chains which only include good covering relations. Yeah. Now, it turns out that the structure of the good covering relations is actually isomorphic to the K Bruhat order, which is a certain subposet of the Bruhat order. And then using all these observations, we're actually able to translate the problem completely into something about the K-Bruhat order. And then at that point, we were able to solve this translated problem using a result of Bergeron and Satilli.
We just want to finish by saying thank you to our mentor, David Perkinson, for helping us prove this throughout the entire summer, and also to Alex Postnikov for suggesting this problem in the first place and for helpful discussions along the way.
Thank you.